Okay, this is what we're doing today. You need to be involved. Determine the relationship between a linear pair of angles. I'll define that. And determine the relationship between a pair of vertical angles. So on first hour, a lot of students got right into the assignment because it's so much easier in lesson 6. We need to go back and hit on some things in lesson 6 before the test, because I know there's going to be test questions. So I have to be careful with that. There is a linear pair. So let's go ahead and define that. You don't have one. You have to actually just lay your iPad down and put a regular protractor on top. That's all you can do. So you should buy one. You should get a protractor. You can use mine, but they're not very good. The whole math department laughed at me when I took those. Because if you have an obtuse angle, you have to really do a lot of work to get that to work. Much easier. Okay, so a linear pair are pairs of angles. So there's two angles that form a straight line. And notice I abbreviate, and I sometimes forget that I'm doing that. I can just use angles with the little angle symbol. So you should write this down, because you're going to see these kind of questions on the ACT and probably SAT that form a straight line. I'm not going to write out straight. I'm going to abbreviate it. And that's why they're called linear pairs. I also call it a straight angle. I don't care. You can use either one because they're both the same. That's an angle. Angles, plural. Two angles. There. Yeah. No, we haven't done the conjecture. Conjecture is a guess. Now, I have a linear pair here. I don't want to call it angle ACD. I can, but it's confusing, for me at least. I'm going to call it angle 1 and angle 2. And what do you think is true about those linear pairs? They form a straight line. How many degrees in a straight line? Look at that. This is going to measure it for me. That's the degrees in a straight line. 180 degrees. So if you have a linear pair, put that right up there. Oh, it won't let me do that? Oh, okay. Then you have angles that do what? They add up to 180 degrees. So doing the problems are kind of fun, actually. Now, this is a theorem. It might not be. It might be postulate. I have to think about it. But how many degrees do we have here? We're going to read this off the inside scale. So that's 110, 120, so that's 115. And now to read the other one, the acute angle. So this is the measure of angle 2. I can put the degrees or not. It's up to you. Don't really care. And then to get the other angle, that's this one, we're going to read the outside edge. That's pretty cool. I didn't draw it that nice. So the measure of angle 1 is, oh, if I can't press it out, I actually have to read it, I think. No, oh, let me do it. I have to read it. So that looks like it's 65. So if I add the measures, that's equal to 115 plus 65. Does that add up to 180? 180 degrees. That's my conjecture. You can't move the little box like I can. So you actually have to write it down. This is called an if-then statement. If this happens, it's a hypothesis, right? If two angles form that linear pair, then the measures of the angles add up to 180 degrees. We're getting ready for life and for higher level math. You can't use the word they unless it refers to something. This said the measures of the angles. What angles? The two angles that form the linear pair. So you have to be really clear in this if part. So if I have two angles that make up a straight line, like that, that's a linear pair. And what's nice about it and we're always going to assume that's straight, even though it isn't, is that they add up to 180 degrees. Oh, some of you are typing. And some of you I did not get the orange sheet from. It's in the no count category, but you can turn it into me by Monday, and some of you will do it today because you just didn't know. Okay, we ready? No. We did it in class yesterday. No, probably not. If you only did part of it, finish it up for Monday. It's not a long assignment. Because I'm just going to give it back to you and say, finish it. Okay, we ready? I did the assignment on the iPad. I didn't think it was too bad. I mean, I did the whole thing, the lesson and the assignment. Okay, here's a conjecture. Two angles form a linear pair, then the measures of the angles add up to 180 degrees. What does a 180-degree angle look like? It looks like a straight line. I'll actually write that out. That we will assume. When you draw a line, even if you don't draw it straight, it's going to be straight. You're going to consider it straight. Okay, which angles form a linear pair here? Which ones make a line? Angle what? 2 and what? And 3. Yeah. Are there more pairs? Angles 3 and 4. Okay, it's critical. Some of you haven't figured this out yet, but it's critical to have that symbol. I just do 2 and 3. I don't know what I'm talking about. You're communicating. This is where math starts, in my mind. You start actually getting math, and things make sense. So 3 and 4 will give you a straight. 1 and 2. That gives you a straight line. Is there another pair, or do I have them all? No, I think there's another one. 1 and 4. And 1 and 4. 2 and 3 are there. And I'll actually color code that. 2 and 3 with these. I think I got them all. So you're going to solve problems finding angle measures using this information. Okay, we have another conjecture. These are about vertical angles. Well, first we have to know what vertical angles are. Now, I would say that you should put this, maybe you want to have a special place on your iPad where you put in your ACT notes. You're going to have to know this on the ACT. And you may already know it. Last class kind of knew it. Vertical angles are angles opposite each other when two lines, I don't like the word cross, I'm going to change it, intersect. A little bit more particular. No, that's a whole picture I was afraid of. Wait. Okay, so which ones are vertical angles? Angles 1 and 3. There's another pair. Where's another pair? 2 and 4. And you're going to see this on the MCA as well. So they're opposite each other. 2 and 3, the word for that would be adjacent. So opposite, you're going like across the room. Now, what appears to be true? I'm going to draw a new diagram. Well, let's actually use, I don't have lines. I have some vertical angles there. Which ones are vertical here? 1 and, whoops, silly me. Angle, it's going to make me do this again. Angle 1 and angle 3, and I have angle 2 and angle 4, and looking at the picture, what appears to be true? Does anything look to have the same measure? Yeah, don't they look congruent? Yeah, they look congruent. So I'm going to say angle 2 is congruent to angle 4. And then somebody said 1 and 3. So that's this one. And angle 1 is congruent to angle 3. And I'm not sure, I want to explain why, but I'm not sure what the easiest way to do that is. If you think about it, it should make sense. But what's going to be true about the measure of angle 1 plus 2? I'm going to do it this way, a little differently than I did in my other class. 180. Then I have another equation. 1 plus 2 is 180. What about 2 plus 3? That's 180 because what kind of angles are those? It makes a straight angle, it's a linear pair. Okay. Now what I'm going to do is a little bit of algebra here. I'm going to subtract the bottom equation from the top equation. Well, I don't like to subtract. I'm going to opposite this, opposite that, and then add. And if I add them, I can't do anything with measure of angle 1 minus measure of angle 3. I can't do anything with it, which is why I love algebra. I couldn't do anything with it. What happens to these guys? Measure of angle 2 minus the measure of angle 2. They go away. That's 0. And what's 180 minus 180? 0. Solving for one of these angles, and I've just shown the measure of angle 1 equals the measure of angle 3. So that's a proof. I would call that a proof. Because I know that the sum of the first two angles is 180. Then the next pair is 180. And if I just subtract the bottom equation from the top equation, I'm going to get 0. Put one angle on one side and one angle on the other side. Okay? Oh, a couple more words. We already did this, didn't we? Complementary angles. You have to know this. Remember what the word means? It's up here. Complementary angles, the sum of the measures add up to 90. Now, here's the problem with this diagram is you cannot assume it's perpendicular. They have to give you a little square. But assuming it is, the measure of angle 1 plus the measure of angle 2 is equal to 90. Or they have to tell you they're complementary. And the same thing goes here. They would say angle 1 complements angle 2, then I know that the measure of angle 1 plus the measure of angle 2 has to add up to 90. Do you remember complementary angles from previous classes? Good. I don't want to spend a lot of time on it. Ready to change? Supplementary angles. You know what? These are supplementary, but they also form a linear pair. And when you look at diagrams, you're going to have to be able to see that. And say, oh, the measure of angle 1, and you may assume the straight line here, sorry, plus the measure of angle 2 has to add up to 180 degrees. That's what supplementary means. They're also a linear pair, so I've got two reasons. They could have told me they were supplementary. Okay, they tell us that these are supplementary, so then the measure of angle 1 plus the measure of angle 2 has to add up to 180. And you can put the degrees in or not, that's up to you. So then what I did in the other class was I said, well, let's see, without using a protractor, do I get a straight angle here? So I cloned this. How great an artist was this person? And we're going to flip this. And we're going to put it over here, and they're a little bit, I can rotate it, but then my bottom line isn't quite right, you know. It's not too bad. But it's not really a straight angle. It should have gone, they should have just done this. But they did it freehand. That's my guess. Okay, I'm going to use my protractor. Your protractors are over there, and I'm not going to get them out. But what about the angles in a triangle? Another fact you have to know. So I'm going to take my protractor here, and I'm going to measure the angles. I'll do the easy one. How many degrees is that? That's 90, right? Never, ever assume, by the way. Okay, so I'm going to call this, move that out of my way, angle A, B, and C. You can call it MHS, you can call it whatever you like. So the measure of angle A equals 90 degrees. And I don't know about you, but I think it's the nature of the beast that we will do the easy one first. The easy one is this one. I thought maybe I had a measuring tool there. That looks like that is, I gotta make sure I'm centered here, 45. Knowing that, what do you think the measure of angle C is? I mean, that was C. Sorry. Measure of angle B. I'm going to say it's 45. Let's see if I can somehow show that with this little guy. And I'm going to have to rotate this. That's why I said this one's harder, but in a way it's not harder, because if I touch here, I can actually get this one. It says 45. When you're in the back, you can't see that, but it's right there. Good. I wish they had it a little bit bigger. Okay, so that's another thing. The sum of the measures of the three angles in a triangle, the sum has to equal 180 degrees. Pardon? Any triangle is always 180 degrees. Well, that's assuming you're on a flat surface. I'm going to actually make a better shape here. Or maybe I'm not. Do we live on a flat surface? No. What we do is we just kind of assume things. Since we're just kind of zoomed in here, it is flat. But if you zoom out, you're up there, on a space shuttle and you're circling the Earth is not flat. It's a sphere. And the geometry on a sphere is different. You don't have to know this, but it's interesting. Different than the geometry here. And there's a posset, which we will get to someday. But it just says, I'm not going to tell you the posset, but if you try and draw a triangle on a sphere, here's a triangle on a sphere. Now remember, those are curved lines now. The equator is a curved line. I can actually find curves or lines here on the sphere so that this is a right angle and that's a right angle. And if you add this angle plus the other right angle plus this unknown angle, is that going to be 180? No, because these are both 90 already. So when I do geometry on a sphere, my geometry is different. So if you are working with space shuttles, you have to be thinking about the geometry that way. Same as if you're a pilot, I would think, because the Earth is curved. So the geometry is different. We'll talk about that. It has to do with the parallel line posset. Not yet. But I just thought it was interesting. If you work on a flat surface, some of the angles of a triangle is 180, but if you're on a curved surface, no, it's not. Okay. What? We just have to do if-then statements next. Is that okay? You don't have to know that. I just think it's interesting. And a lot of people don't know that. They're always 180 in our world. We're always doing geometry on a flat surface. You guys know Einstein's theory of relativity. You've heard of it, right? Yeah. If we go slow enough in your physics classes, distance equals rate times time. If we go slow enough, if we speed up very fast, everything changes. All the rules change, and the physics becomes very different. So it's kind of the same thing. We zoom out and we look at the Earth, that postulate doesn't work anymore, or theorem. Okay, these are if-then statements. If two angles form a linear pair, always you end a if statement with a comma. I didn't know that. Then the measures of the triangles the measures of the angles add up to 180. If two angles are vertical angles, notice I'm going to be real specific. I'm not going to say if the angles are vertical. If two angles are vertical, then their measurements are the same. They're congruent. When I took geometry back in high school, we had to have these things memorized to the word. I can say then they have equal measures. I can say then they are congruent. Or I can say they have the same measurement. It doesn't matter. Okay? It doesn't matter how you say it. I'm not going to make you memorize it and say it, to a perfect memorization. Okay, we have an if and a then statement. There's a hypothesis and the conclusion. The hypotenuse is the if, and the conclusion is the then. The if is what we know, what we're given. Somehow we're going to know that. So this is the hypothesis, and notice I'm being lazy, aren't I? I'm not going to write it out. This is the conclusion. Hypothesis is what you're assuming to be true or you know to be true. From that, I can make some conclusions. If I have two lines that are perpendicular, if two lines are perpendicular, we should know that. Do you guys know the symbol for perpendicular? It's this little cross thing. That means perpendicular. That little symbol there. You can write it out if you want. I don't want to write it. So if two lines are perpendicular, what conclusion can you draw? What's true about these angles here? They're all right. Then the lines form right angles. I want to write it out. So if I know lines are perpendicular, then I know I'm going to have right angles. And if I know I have right angles, and I have another ray in here, okay, I know that's a right angle. What's going to be true about the measures of angle 1 and 2? It might be 45, but what do they add up to? Add up to 90. That's what you mean by proof. That would be another conclusion I could say. Angle 1 is complements angle 2. I found two conclusions I can make. That's what makes geometry a little bit hard. Okay, so what's the hypothesis here? Two angles are vertical or they have equal measures. This is the hypothesis. This is the conclusion. So we're going to be using if-then statements. Now, this is probably a new word for you. Converse, have you seen that? All you do is flip the if and the then. That's it. But the problem is you have to worry about the English. So right now, my if, two angles form a linear pair, and the measures add up to 180. I want to reverse that. I'm going to do the first one with you. The second one I want you to try. So I want this now to become my if, and this to become my then. The hard part is how do you write it? Because I can't say if the measures of the angles adds up to 180. I don't have three angles or four angles. I have two angles. So if the measures, and I do write fast, although I think it writes pretty fast on the iPad, of two angles, you've got to get that in there. After I refer to the two angles, then I can use the word they. If the measure of two angles equals 180, or I can say adds to 180, if I can understand what you're saying, it'll be okay. Then, now I don't have to say the two angles form a linear pair. I could if I want, but now I can use the word they, because it refers back to my two angles. So you have to identify things in your if statement. Then they form a linear pair. I think this is the last one that we get into homework. And we'll do problem together. Now the question I have for you, is that statement true? I know my original statement is true. If I have two angles that are making a straight line, then I know the angles add up to 180. But what if I have two angles that add to 180? What if I have this? Here's angle 1, and here's angle 2. And I'm going to tell you that the measure of angle 1 plus the measure of angle 2 equals 180. Do they form a linear pair? No. They don't form a straight line, not unless I move them. When you say they form a straight line, means they're already there. They're not already there. So guess what? This is not a true statement. For something to be true, it must always be true. It might be true, but there's no guarantee. Again, that's a life lesson. If you reverse an if-then statement, the converse is not necessarily true. And you can take classes on that. It's called logic classes in college, and they're kind of fun. Okay, can you guys do this one? If two angles are vertical angles, this is our hypothesis. This is what we want for the then. And this is what we want for the if. But you can't use the word they. You're going to have to be specific. What does they refer to? Give you a chance to try it, and then I'll write it. Or have you already done it? And that's the last thing. Anybody want to come up and write it? Somebody want to at least read what they did? Okay. What'd you write? If two angles, you either say are congruent or have equal measures, your choice. Which one do you want to use? Two angles are congruent. Now, this is how lazy I am, and you can be just as lazy as me. I'm not going to write the word congruent. I'm going to write the equals and the little similarity symbol above there. So if two angles are congruent, then what can you conclude? They are vertical angles. And actually, I have had students come back and tell me, by the way, I spelled vertical right. It's cal, like in calories, A-L, not L-E. They've come back and told me that they've used the logic from their geometry class with their parents and to get things. Well, if this is true, then that's true. Your parents do it to you all the time. If you clean your room, then you get to go to the football game tonight. I've heard that one before, right? Or something like that. And that's it. That's what you do with if-then statements. Is this a true statement? If I have two congruent angles, are they vertical angles? Not necessarily. Excellent. Angle 1 is congruent to angle 2, but they're not vertical because they're not connected. So that's the problem with the converse. And that's it. Whoops, wrong one. There's your first, that's the assignment. And a lot of kids just went right into that, did not want to go over the homework. We got to go over the homework on lesson 6. Okay, so there's a picture. I think your picture is probably a little bit better than my picture, but I'm not sure. Without using a protractor, yes. Well, what's the measure of angle A? Why? Why are these congruent? They are what kind of angles? They are not, they're vertical. So angle A is 60 degrees. And why is that 120? That's correct. Because, so really, anytime you make a statement, you better be able to tell me why. I'm not going to ask you why all the time. But when you go into your upper level classes, and I don't care if it's math, it might be something else, you might have to explain why. So this is 120 degrees, because these are linear pairs. So how big is C then? How big is C? 120. Okay, let's see. They're kind of fun problems. I did mine all on the iPad. I didn't think it was bad at all. Now, what I might do, oh, and then they asked me, now, by the way, on number 8, see that tree there? That tree is perpendicular. That is a right angle. You need to know that. The tree is not at an angle at all. It's perfectly straight relative to the ground. And then the other class asked me about this. Let me give you a hint. It says pattern continues. What's the rule for the perimeter, not the area? So be careful with that. And of the nth rectangle, what's the perimeter of the 200th rectangle? Oh, so we have to figure out what we're going to relate here. This is figure 1, figure 2, figure 3. So that's figure 200. Okay? So that's the number of the figure. When you're talking about the 200th rectangle, which one are we talking about? And then I'm going to find the perimeter for each one of these. And it'll be obvious when you do it, if you do the arithmetic right, it'll be really obvious to you what the pattern is. Now, finding B might be a little bit trickier, but it's a linear pattern, and we are responsible for those. The other ones you're responsible for is recognizing the handshake problem. So this is the homework. Lesson 7. Some people have already probably done it. So it wasn't too bad to do. But let's go back here now, and let's look at lesson 6. Okay? Now, my other class made me go back and redo question 2, but I don't think we need to do that, do we? Okay, so we did, oh, yeah, this is in the class. We did this one about dividing into regions. If you want me to do it again, I will, but we already did do it. We should have done it. So I'm going to clear the ink, and let's do this one. Now, there's a little problem the way the question's framed. 3 and 4 is the same question. But what they did with 3 was they tried to give you some help and say, answer this question, how many diagonals can you draw from one vertex? Well, what if you draw all the diagonals in the problem? This is just like the handshake problem, but it's a little bit different. So we have to label some things here. This is the number of vertices you have here, number of sides. Let's call it sides. And then this is the number of diagonals. I mean, I'm assuming some of you had some problems with this. Or did you all get it? I don't believe that. I think we should do it. Then we have a 4-sided figure, a 5-sided figure, 6, 7, 8. And then we're going to do 35. Well, let's do n, and then we'll do 35. How do you do this problem? You start with an easy one, the 3-sided figure, and you look for patterns. I'm going to find the patterns in the table. So if you have a 3-sided figure, here's your vertex. These guys are my neighbors. I'm the vertex. We're a triangle here. Diagonals go across the figure. You guys all know what a diagonal is. There aren't any diagonals, are there? No. So there are no diagonals there. Now let's choose one vertex. How many diagonals are there? It can only draw that one. I can't draw it to my neighbors. Not allowed. And by the way, this is what discrete math is about. And you get a lot of this in probability and statistics. So if you're not fond of it, I'm telling you, that's what you're going to be doing. Not all of it. There's a whole bunch more to stats. But you'll be doing this problem probably again in higher algebra. So from this vertex, how many diagonals can I draw? 2. I have 0. I get 1. I get 2. Guess what I should draw? I should draw a hexagon. And I'm going to pick one vertex. And what'd you say? 1, 2, 3. Lots of ways to see the patterns here, because there are multiple patterns here. I can look at this way. This one's 0, 1, 2, 3. You can tell me that. 4, 5. I'm stuck. I can't do that one. But can I look at my patterns vertically? What's the relationship between these numbers? 4 and 1. What's the same relationship? 5, 2, 6, 3, 7, 4, 8, 5. Somebody said it. And minus 3. So this is going to be 35 minus 3. I don't really care if you do the arithmetic. Because my goal here is to get you to see the patterns. And that's all there is in that. Now, hold this thought. So we're going to use this on the next part of the problem, which we call question 4. Question 4 is asking how many diagonals can you draw in a polygon, period. Okay, let me clear my ink. There we go. So I want the total number of diagonals I can draw. So this is the number of sides again. This is the total number of diagonals. Well, this one's pretty easy. 3 sides, there aren't any. You can do this part. All of you in here can do this part. Okay, from this vertex, I can draw 1 diagonal, right? What about the next vertex? We are going to allow doubles. What we'll do is just divide it out at the end. So that's A, B. What about vertex B? How many diagonals can you draw? 1. We just did this in the last part, right? How about C? How many diagonals can you draw? 1. And D, how many can you draw? Do I have all my colors doubled? Yes. But I don't want the doubling. I only want it 1 time. Well, from each diagonal, you're going to draw 1 plus 1 plus 1 plus 1, because there's 4 of them, right? And we have to divide by 2. Still not clear yet. A, B, C, D, E. And that's why I say feel free to use my colored pens and pencils, but you actually have colors on your iPad. So it's kind of cool. So from each vertex, there are 2. That's right. It's 2. And what about at B? I got this. I can do 2 at B, right? I can do 2 at C. I can do 2 at D, right? Have I done D yet? Oh, I'm looking at the original one there. I can do 2 there. And I need a new color. Oops. And I can do 2 at E. 2 colors there, 2 colors there. I get a beautiful star. But I don't want all the double colors. So we'll take that answer and we'll divide by 2. Can you think of an easier way to add the 2's up? How many 2's are there? It's 5 2's times 2 and divide by 2. Without drawing the 6th figure. If you need to draw it, draw it. It's still not too complicated. This was 2 times 2. Sorry, is that right? Excuse me. 4 times 2. No. Wasn't times 2. Silly me. It's 4 times 1 divided by 2. So if I do 6, what's the first number going to be? This was 4. This was 5. This is going to be 6 times. How many diagonals can you draw from each vertex? 3 less than the 6. So you see 1, 2, 3 divided by 2. I don't care what the number is. What's 7 going to give us? 7. And 3 less than 7 is 4. Have you seen the patterns? This will be 8, 9. Sorry. Oh, hang on. We're going to get there. And then this is 5, 6. So what's n? Well, what's the first factor or number? N. And how do you relate these guys? You just did on the last page. N minus 3 divided by 2. Now you can put the 35 in. So it's 35 times 35 minus 3, or you could say 32, I don't care, divided by 2, and I don't care if you multiply it. Because it's a great question, are these numbers related? 5 and 2, 6 and 3, 7 and 4, 8, 5, 9 and 6. It's that number minus 3, which is what we did on the last slide. I wish it was all together on one slide. We just subtracted 3. Remember this problem we just did before this? Remember? Question. Minus 3? Because you can't draw a diagonal to yourself. You can't draw a diagonal to the neighbor on the right, and you can't draw a diagonal to the neighbor on the left. That's why it's minus 3. And that's what we do in a probability class. Hard to teach. because it's times, because if we look at the patterns here, because there are 5 vertices here, so for each one, there's 2 diagonals. I could add 2 up 5 times, or I can use short notation, which is multiplication, but that's really 5 times 2. I don't have a pen. That's really 5 of the 2's divided by 2. I'd rather see this than the actual numbers. I don't care about the numbers. Because the numbers, I don't see the patterns. And you'll be doing this in a lot of classes, actually. Oh, I haven't watched. How about that one? Oh, we did that one. Didn't we do that one? I think we did. Those were the lines. No, how many line segments? Oh, no, I didn't do that. Did you guys get this, or do you need help with this one? You got to tell me. You got it or not? I would make a table, and I think there's one person who's got the question more than you. I love those tables. Aren't they cool? Okay, forget the 35. Let's do something simple. Okay, we do not have collinear points. We're going to put points in a plane or on a piece of paper and draw segments to connect each point to all the others. So if I have 1 point, I can't draw any segments, right? Number of points. Number of segments. Because once we do this, we get to the end problems, which we might not get to till Monday, and that's okay, because Monday's lesson's not that, well, not that long. I wanted to get these back. Okay, there aren't any line segments. 2, how many line segments? Well, you can draw this one, but guess what? You can come back. Can't you? No? But we have to divide by 2. We don't want the duplicates. So it's 1. How many line segments here? I can do this and this. Does anybody recognize the problem? It's the handshake problem. But you know what? If you don't see it, you just do it. And, oh, I did that one already. Where's the other verb? Oh, this one. And that one. Yeah, there we go. And so we had 3, and so we have 1, 2, 3 segments. And you know what the next one's going to be. How many segments? 1, 2, 3, 4, 5. I don't know. I can't count. 6. I don't know. They just chose it that way. This is the handshake problem. What's the formula for the handshake problem? N times n minus 1 over 2. So it's 35 times 34 over 2. Leave it, or use a calculator. Who cares? That's what you have to do, is take a problem and relate it to the handshake problem. You will not have a diagonal problem. You don't have to recognize that one. That's the one I did. Positive I did in both classes. So then somebody came in and asked me this question, and I wasn't sure what the question was asking. Once I got that figured out, it's easy. If 40 houses in a community all need direct lines to one another in order to have telephone service, how many lines are necessary? Sketch and describe 2 models. First model, the situation in which the direct lines connect every house to every other house. Anybody recognize this? We just did it, didn't we? Here's 1 house. Here's 2 houses. You have to connect it this way, and we connect it that way, but we don't want a double connection. We don't need it. We divide by 2. Is that sounding familiar? What if I have 3 houses? It's the handshake problem. Let's see. 1, 2. 1, 2. It's the handshake problem. Okay? Not very practical, but it's n minus 1 over 2. We'll cheat a little. You know what? I said you have to recognize the handshake problem. So if you don't know what it is, it's the handshake problem. So now there are 40 of these dots. This is 4 dots. I have 40 of them. So you put 40 in times 40 minus 1 all over 2. Mm-hmm. I don't know. Whatever that is. Which is a calculator. I'd leave it like that. I would do half of 34. It's 35 times 17. Oh, I just have to multiply. Not, okay, I hear your question. Did I add it right? Did I multiply it right? 615. It is not distributive property because distributive property would be this, 35 plus 34 with the 1/2 out in front. You distribute multiplication over addition, but you do not distribute multiplication over multiplication. So the distributive property does not apply. That's associative property, what you're doing there. You can't distribute this. There's no subtraction here. If you want to multiply this out, you can. You want to do this? Now you can. But I don't know why you want to do that. Minus 3n all over 2. That's more complicated because now I got to square 35 and take 3 times 35, and that's not easy. Yeah. But those are good questions to clarify some of those little details. Hopefully you'll remember it. Okay. I am going to hand these back because I want them back to you. Your job is to, because the assignment isn't that long, I don't think it's very bad, but it's to look at, we have 8 and we have 9. 9 is tough. 9 is a handshake problem, but you have to solve for n. This one? I don't know. That's what you have to do. Well, that's why. Because these are people. You can't have a negative number of people. One's going to be one's negative 12 and one's positive 11, I think. I don't know. Haven't worked the problems. I don't know the numbers. Where's my answer book? 66. Okay, so first now this feeds right back into that distributive property again. I would multiply by 2 here and by 2 there. I either can reduce the 2's and then distribute, or I could distribute, but you can't distribute the n and then distribute the 2. It's not going to work. So this is n squared minus n equals 66, 12, 132, right? Minus 132 equals 0. When you solve any equation, I don't care what equation it is, it's always relative to 0. Okay, I'm going to guess it's this, right? So n is equal to 11 or n equals negative 12. Well, that's the number of people. You can't have a negative number of people. No, I got 11, but your answer was 12. Oh, well, then maybe I have it backwards. Oh, I do have it backwards. Because this doesn't give you this. If you multiply that out. Yeah, so 11 is right. No. If you multiply that out, you do not get that. It's n minus 12 times n plus 11. Oh. That's why.